So what we're about to do is shift our attention from concurrency and threading and thread pools to the synchronization side of the house. And this will then start preparing us for the next programming assignment, which will use a couple of variants. So this is getting a head start on what we'll cover for the next assignment, assignment 2B. We're going to start by talking about something called a ReentrantLock, and I'll explain what the concept of a ReentrantLock is by giving an overview of things called mutual exclusion, or a concept called mutual exclusion. And I'll give you a human known use of mutual exclusion. I probably already used this before. So mutual exclusion, which is sometimes abbreviated as mutex, defines a critical section. And a critical section is just a group of instructions or a region of code that must be executed atomically. In other words, one thing at a time, all or nothing. Kind of like the discussion we had before about atomic operations, but this is really intended to cover a broader range. An atomic operation is like add 1 to this number or add n to this number. So they're very short. This is potentially an arbitrary region of code that needs to be done atomically. How do we ensure that atomic properties are preserved? We only allow one thread at a time to run in this block of code. So the way it works is you come in, you acquire the lock. If the lock is not available, you have to wait, but you acquire the lock when it's available. Then you come in and you run. And if any other threads come along while you've got the lock held, then they will be kept at bay. They will be unable to proceed until you're finished doing your thing. And what your thing is typically doing is updating shared mutable data. So you're typically either reading or writing data that is intended to be accessed atomically, so you don't want anybody coming in and corrupting it. And you want to avoid race conditions, you want to avoid consistency problems, you want to avoid visibility problems, and so on and so forth. Other threads that are waiting have to obey this locking protocol in order to access that shared mutable state or shared mutable data. Otherwise, chaos and insanity will ensue. If they choose not to obey the protocol, then bad things will happen. And those bad things would be race conditions. So race conditions, as we've talked about many times, arise when a program depends on the sequence or timing of threads in order for it to operate properly. So you don't want to have race conditions. You want to have multiple threads colliding and trying to simultaneously update or read the same chunks of memory. When one thread, the current owner thread, leaves the critical section, another thread can enter and start to run. And this is really at the heart of what we were doing with the spin lock. We were doing the spin lock in order to implement a critical section, because we were making sure only one thread could be in, other threads would be waiting by spinning, and then you would go in, do your thing with the hash map. When you're done updating the hash map, you release the lock, and someone else can go in there. So that's the whole point, acquiring and releasing regions of code. Same idea, the other thread comes in, threads that are waiting have to stay out of the critical section, it does its thing, and so on. Under the hood, a mutex is typically implemented in hardware, and it typically uses atomic operations, at least for the fast path. And these atomic operations, which are the atomic compare and swap operations we talked about earlier in the class, will either work or not work. They don't leave things in some inconsistent, half-baked state. And that is true not just for one thread, but through the whole caching of state in different threads and different cores. So it ensures that things have a consistent and visible and corruption-free state. And all the stuff we talked about before, like compare and swap in the unsafe class, is used under the hood to make sure this actually happens. And these methods, as we talked about, are wrappers around the underlying hardware instructions that do this kind of stuff. There's many examples of mutual exclusion in everyday life. My favorite one, because it's memorable, is the Restroom Protocol on an airplane, where you're obliged to wait while the restroom is in use. And basically, here's how it works. When the sign says vacant, one person can go in. They then lock the door, so they're inside there. Anybody who wants to come along and they see it's occupied or locked has to queue up to wait. And then when the person is done, they leave, the lock goes back to being vacant from being occupied. And this protocol is fully bracketed. If you recall our discussions about semaphores, we said that some uses of semaphores are fully bracketed, some are not. All uses of mutexes have to be fully bracketed. The thread or the person that acquires them must be the one to release them. And then at that point, someone else can go in. Is it the next person in line? Is it the crying baby? It all depends on various things. But the point is that only one thing is in there at a time. So that's the end of our overview of ReentrantLock.